Yeah, so thank you for coming after conference dinner yesterday. I'm just very motivated to be here. I'll try not to disappoint you. So I will start by thanking the organizers for inviting me here and for organizing this very nice workshop. So I guess this is Tommy. I would have liked to say Lavinia, that is also like this. And so some of you already know that well, this is kind of interesting day to give a talk. First of all, because yesterday was my birthday. That's only important for me. But tomorrow is a pie day. So we are going to give a talk in pi minus 1 day, which is nice. At 9:26, it will be even more accurate. And even more, tomorrow is also Einstein's birthday. So today is a very special day to give a talk. So I'm going to talk about this Born-Infeld-inspired way of modifying gravity. It's quite different from what we've been seeing in the Greek here. And it's based on the work that I've been doing recently with Gonzalo Olmo, who is in Valencia, who now is enjoying some nice time in Brazil, with Lavinia here, and Christophe Langevin, who was my boss in Rwanda. Okay, so this is more or less the outline. I will start by very briefly introducing the Born-Infeld theory of electromagnetism, and we'll explain a few interesting features of this theory, and then how this led to some modifications of gravity inspiring the same determinant form. Then I will move on to our proposal to generalize this kind of axioms, and I will very soon focus on the minimal extension, what we call minimal extension, and I will explain what this is. Then I will study some perfect fluid and cosmological solutions, and I will use these cosmological solutions to develop this kind of inflation that is supported by a dust component. We will see how. Yeah, okay, so this is easy. This is Maxwell action, we are familiar with that. And well, it's very nice, it provides two distributions, spin 1, blah, blah, and it describes electromagnetism. Very good. So the problem of this was for a point-like particle, the self-energy diverges. And then this guy is born on Infeld. In some works they use what they call the principle of finiteness, and it's based essentially on this usual tree. What you use when you go from classical mechanics to relativistic, you introduce this square root structure, this new constant, and then you set an upper bound for your velocity. So you can do the same with this action. You introduce this square root structure, and then naively you would expect like an upper bound on the allowed electric field that you can have. And then you can hope for this to regularize the self-energy of your particles. This was not very satisfactory for them, because well, when you go from here to here, there is a motivation, and it's the Lorentz transformation. You have a symmetry, and the line symmetry here that tells you that this is what you should have. And then, motivated like this, they say, okay, so then let's try to modify it, but in this form. Because if we know that if we introduce the determinant of some rank 2 tensor here, then this is an invariant volume. So let's play with this and let's see what we find. And then after a few steps, you can know that this is like the simplest case for this kind of modification. Okay, this can be written in different ways. So you can expand this determinant, you can write it like that, or now you can use the electric and magnetic fields, and you can write it like that. And well, you see that this is what you would naively introduce to regularize the self-energy. Then, first thing to check is that when the electromagnetic field is small, you recover Maxwell, and this is the case, no? Because well, you expand this, and you have this one will go with this. You have 1/2 on the square root with this minus, and therefore they will away, and then you obtain Maxwell. Okay, this. Well, now there is a modification when these terms become relevant, and what you see is this is a plot from the original paper, and then you see the 1/r behavior here of Maxwell that diverges for r equals 0, and the solid line is the Coulomb potential for this theory, and it goes to a constant. So you regularize with this structure the divergences that you would obtain in Maxwell. It has some interesting features, like well, in Maxwell we know that there is this electromagnetic self duality, And this is also the case for this Born-Infeld action. To see this, well, any non-linear dynamic can be written in the equations can be written like this if we introduce this H and D vector. So, for example, the Maxwell equation, but for this H and D. Then you have this Beltran transformation. If you plug this here, then you find out that for the theory to have this invariance, you must satisfy this relation between E and B and D and H. And this is the case for Born-Infeld. Some other nice properties is that it has causal propagation, because there is this non-linear terms here, and the absence of shock waves, and I never know how to pronounce this, birefringence, something like that. And well, apparently people in field theory call this kind of theories exceptional theories. And this is the only regular exceptional theory for electromagnetism. It's also nice that there is exact finite energy soliton solutions that are called ions. And well, it also arises in low energy limit in string theory and the brains, and well, you can understand because well, this determines the structure that you usually find in the theories. Okay, so this inspired Desser and Gibbons to try to use the same trick. This time, the motivation was to regularize cosmological or black hole singularities. And then, well, you play the same game. You introduce the square root of the determinant. Here you have the metric, and here you have the Ricci tensor. And then you have to introduce these higher order corrections. They will start at quadratic order, and you have to tune it order by order to remove the ghost that you will encounter here. Because this is formulated in the metric formalism, and then it will give you higher order equations of motion. Yes.
Wasn't this kind of thing written earlier by Robert Brandenburger?
Not exactly the same form.
Not the same form?
Yeah, but the same idea.
Yeah, the idea was the same.
The idea was the same.
Okay.
We didn't worry about, for example, we didn't worry about ghost fields. We wanted bounded curvature.
Yes, that's what.
There's a limited curvature construction.
Thanks. Yeah, so then you will find higher order equations of motion, and then you will have a ghost. And then you have to tune this order by order, you can expand it, and choose this x mu order by order to cancel all the higher order derivative terms that you will encounter. The problem is that there is a large freedom in the choice of this, because well, each order you can fix it in many different ways, and there is no clear immediate criterion to fix it. They argue that you should choose this x so that your theory has this the analogs of Coulomb solutions, so it regularizes Darcy solutions. They also say that the resulting theory should be supersymmetrizable, things like that. But they didn't develop this as far as I know. The nice thing is that this determinantal form for gravity was already considered by Eddington in 1924 as a purely affine theory for gravity. So here you don't have a metric, and the invariant volume is determined by the connection, by the symmetric part of the Ricci tensor of an arbitrary connection. The problem with this theory is how to introduce couplings to matter, because if you don't have a metric, how do you construct the kinetic terms? And then in this paper, they argue that you can use a metric to construct your matter Lagrangian, and then the metric will only enter algebraically. So now you can compute the equation of motion for the metric that will determine the metric algebraically, and then you can plug it back here, and you will have a purely affine theory, including matter. Now, since we are talking about the Palatini, let me briefly remind you, because you will do it in more detail later. No? Okay. So, a general connection can be split like in these three pieces: the Ricci-Vita connection of a given metric, so rank 2 is a metric tensor, and this determines also the non-metricity that determines this part of the connection. So yeah, I put this here because these two are related. So this non-metricity is associated to a metric tensor. And this last piece here is determined by the torsion that is in the symmetric part of the connection. And what this trivially satisfies the homogeneous solutions of this equation. So we know that for Einstein-Hilbert, the metric and the Palatini are equivalent. So the field equations will tell you that the connection must be the Levi-Civita connection of your space-time metric. And well, this is general for not only for the Einstein-Hilbert, but for all the log-log invariants. You find the same result. And I would like to point out that if you have a general connection, you have different traces of the Riemann tensor that you can take. This is the usual Ricci, but then you have this, I think it's called Ricci tensor. And if you have a metric, you can also consider this 1-1 tensor, and this is called homothetic tensor. Okay, so then, inspired by this, in this paper, he considered this deterministic form for gravity, but now we don't need to introduce this h mu, because we are going to consider this in the Palatine formalism, and then we don't have the problem of the ghost. Essentially what happens is that the connection typically can be algebraically solved in terms of the matter and the metric. So it does not introduce additional degrees of freedom, and you don't have a the equation of motion. The nice thing of this theory is that, as shown in this paper, it has a bouncing solution. So this is the scale factor, it's a function of time, and we see this bouncing here. We have several branches, but only one of them you have the bouncing. The problem with this is that at the bounce, the tensor perturbations are unstable. So there is a divergence here for tensor perturbations. It was shown in this paper.
So, okay, can I ask you, so if the Palatini is algebraic, we can just integrate that and get back to metric language.
Yes.
Then we know in metric language that anything over level up as it goes.
Yeah, thank you for the question. I forgot to say. So usually what happens in this series is that low curvatures is called general relativity, and at higher curvatures you still have Einstein-Hilbert, but not for the space-time metric, but for an auxiliary metric. And then essentially what you change is the couplings to matter.
Oh, I see. So it's a field reduction from Einstein.
Yeah, so the couplings are
Okay, but even then the couplings to matter, then curvature.
I don't know.
What else is there?
Couplings to matter, why? Will they depend on curvature?
Or what else do we find?
No, sorry. So I haven't done it, but my guess is that if you do it, you will obtain Einstein-Hilbert, but for an effective metric, and then this effective metric will couple in a strange way to matter. But this will not depend on the curvature.
But how do you construct the effective metric? Because the effective metric has to be built out of covariant quantities, so the older metric and the curvature.
From the equations, you obtain that this is not always the case. It's in some theories. You obtain that the connection is the Levi-Civita connection of some auxiliary metric, not the space-time metric. And this auxiliary metric is the one that will have the Einstein-Hilbert term.
But then I can perform a field redefinition for that metric. I'm always allowed to do that. So then the complication is in the coupling to matter.
Yes.
Yes.
But then the same story applies. Then you're coupling to matter over the normal one, I suppose.
No, because then you don't have higher the equation.
But anything, even if I just change square root of minus g to minus g to the third, then probably only suppose.
So maybe let me go through the equations and then we can discuss. Because my answer is based on the equation of motion. So I never integrated out the connection to see what the result in action is. But from the equations, that's what we obtain. But maybe let me go on.
Sure.
Yeah. Okay. So now our proposal to extend this theory is based on this very simple observation. It is that if you take this, you can take out the metric here and to put here, and now you commute the determinant on the square root, and then you see that you can write the axiom in this way, where you introduce this round 2 tensor here, and then so some of you might be familiar with massive gravity. if you are not, I will remind you that the interaction terms look like this, and they also have this square root structure of G minus 1f, the same. But now here you have a linear combination of all the elementary symmetric polynomials, and here we only have the highest of them, so we decided to consider a linear combination of all of them. So this is the theory, this definition of this characteristic polynomial, and then this matrix M is given by this square root structure. Well, here we encounter the usual problems of defining the square root of the matrix. We will assume that this is definite positive, and then M is the only definite positive square root of this matrix. Concerning couplings to matter, we will assume that they are minimally coupled. Okay, so to the spacetime matrix. Okay, so now first thing to check is that the curvature limit. We will cover this cosmological constant and this effective Newton constant. This will fix one of the two free constants here in the action. By setting this to Newton's constant. Well, it's also remarkable that we obtain the usual projective invariance of Einstein-Hilbert action, but in this case it's only accidental because higher order terms in general will break it. Well, this is because the full theory does not have this invariance. Only if you choose here the symmetric part of the Ricci tensor, you will have the symmetry in the full action, but not in general. So the differences will appear in the high curvature limit, and well, we have these messy things. I will only notice these two cases. Well, for the highest determinant, we obtain Eddington's theory, and this is a case that I also find particularly interesting because well, you modify Einstein-Hilbert without introducing additional dimensionful constants, and so if you interpret this trace equation as some kind of expectation value or something, this will be like the variance of the square root of G minus 1 half. Maybe it's obviously wrong. Okay, so these are the field equations. They are maybe not very pretty. Here I only want to point out that for all the terms we obtain the same structure for the equations. So you have this W that is like a fundamental object of this theory and is given by this, where F1, F2, F3, F4 are given by this. So it's very complicated, but the structure of the equations is the same for all the terms. Okay. So now I will focus on the simplest case, and that is only the two first invariant polynomial, so the trace constant. We need to introduce this so we have Minkowski as a vacuum solution. Okay, so so maybe after this we can rediscuss. So you take the metric field equation, you obtain this equation, and if you use the definition of M, you can rewrite it like this. And then in principle you can solve this for n and express it algebraically in terms of the matter content and the metric. In many situations actually M can be expressed in terms of G minus 1t, or if you want t half that, or rho and p. Now you go to the connection field equations, you have this, and we are going to consider solutions without torsion. Okay, and in this case, this W is simply the inverse of N. Then, if you don't have this, okay, you have these two terms. Now you trace over lambda and nu, and you get that the divergence of these vanishes because you get the same here and there. Then you go back to this equation, you see that this is 0, and then you obtain that this term here should be equal to 0. Now you can split it into symmetric and antisymmetric part, and then for the symmetric part, you see that the connection is the Levy-Civita connection, but of this auxiliary metric, which is not really related to the metric and the matter content through the metric field equations. And then for these torsionless solutions, this will be like a consistency equation. And now we can come back to it.
It seems like the matter coupling has nothing to do with it. Let's set the matter coupling to 0 and just ask whether the gravitational theory is goes free. So if we integrate out the connection, you get some Lagrangian that just depends on.
So you mean in vacuum?
Sorry?
In vacuum.
In vacuum.
Yeah, in vacuum is equivalent to GR.
It's
zero.
It's 0?
GR.
GR.
General relativity.
Oh, okay.
Even with all your this form.
Yeah, I'm going to show that in probably next slide.
So if it's GR in vacuum, then you're just changing the coupling to matter.
Yes.
But then the point holds. Any change coupling to matter must be some function of G and R and derivatives R and so on and so on.
So I don't think so, because in the end matter will satisfy second equation of motion. So there might be ghosts, but not stochastic ghosts.
No, there's still astrophysical because you put a background there for the matter field, then the matter equation of motion is hybrid. The metric equation of motion is hybrid.
But they are not, because all these equations are second order.
But if you include matter,
Yes.
so maybe the kinetic term just is just 0. But then in coupling matter, if I couple to G mu plus the Ricci scalar, the Ricci tensor, for instance, then when you derive.
I don't think, I might be wrong, but I don't think that's how it goes.
What can matter couple to?
So I don't think it's the Ricci that will couple to matter.
So do you couple G tilde to matter in a standard way?
No,
G is coupled.
G is coupled in the standard way.
But then you're saying that it's Einstein theory without matter is Einstein coupled in terms of G tilde. Right? So I can just redefine my metric and call G tilde my metric. So then I should just write G back in terms of G tilde. So now the matter is coupled to some non-trivial function of G tilde. And any coupling other than the minimal one will give you back a ghost.
But you mean because there will be non-linear couplings to the auxiliary metric? So imagine
this M depends on your energy momentum tensor,
on rho and P. Rho and P.
Yeah, so it's some kind of, matter couples to this metric in some kind of non-linear way. It's not dependent on the reaches, but on this energy momentum from the matter itself. Some kind of strange coupling, but not necessarily with the curvatures. So it's
well, even if it's just a function of G other than the normal one. I mean, what else can it be other than the normal one?
M has Ricci, no? Because it's the...
Yeah, M has Ricci in it.
No, you have solved for this in terms of rho and P. So this is a function of metric, rho and P. So there is no curvature here. This should be regarded as a function of rho and P matter.
maybe we could proceed because otherwise it's discussion.
Okay, so R there is Riemann.
Is the Ricci.
Just Ricci.
It's Ricci, which only depends on this theta, and then when you use the equations of motion with respect to the metric G, then you can solve M in terms of rho and P. But you can do that only if you have a symmetric. So for specific.
No, but now you have the equations of motion. It's not the same. That's not the same. Okay, but you should carry on anyway.
Algebraic. Yes, algebraic.
No, but, so I understand the concern. So the concern is that
equation of the gamma is
yeah, so the point is that to do this, you need to use all the equations. So not only the equation of the connection, but also the metric field equation.
Yeah, that's the problem, because you shouldn't plug these equations of motion back in the action.
Yes. Yes, that's why I'm saying that I didn't do it, and this is my guess. But and this is based on the. So you can always integrate out the connection, I guess.
So I think you want this. Yeah, so you want to say that R you can write in terms of G and T, the stress energy, and then you can plug that back in, and in the end what would happen would be some crazy Lagrangian for the matter.
Yes, yes, exactly.
Okay.
Let me. Yeah, so this is in vacuum. Well, it's more general. You can take this Einstein space answer, and then this implies that the fundamental metric is proportional to the identity, as it should. And we are going to call this m squared. Then you go to the metric field equation, and you obtain this. Now, k in principle could be an arbitrary function, but from here you see that if you take the covariant derivative with respect to the Levi-Civita connection, the metric, then this vanishes because it's minimally coupled to the metric, and then you see that m should actually be a constant. And then if this is a constant, this can only be supported by a cosmological constant. And then you can go to the connection field equations and compute your auxiliary metric, and you see that it's conformally related to the space-time metric. And well, if you have an arbitrary cosmological constant, you can solve this equation, and you typically find two branches. One that is continuously connected with GR, and that's the loop, this one. This one, because m goes to 1 when rho is 0, and that's what you should obtain. And this is the curvature. And well, since this is m squared, we see that even though we have all these features here, only this part is physically, well, so this is the physically meaningful branch. So we should disregard this part here. Okay. Now we can go to a more interesting situation where matter sector is just a perfect fluid with rho and p. Then we take these answers for the fundamental metrics. And then again you go to the metric field equations and you obtain these equations for n0 and n1 in terms of rho and p. Then you can solve this equation. And in general we find three branches of solutions, but for the same reasoning as before, so positivity of this metric, only two of them are physical. And out of those two, only one is continuously connected with GR. Let me show here. So this is m0 and m1. This is for different equations. Well, this is 1/3, because you cannot see. And then well, we have all these branches here and there. And well, I'm highlighting here the physically relevant one. Here we have these two. And for rho equals 0, m should go to 1. That's this one. And the same for m1. And the same for matter. Well, this equation of state, which is essentially the same as cosmological constant. And these are, so I've chosen these values, but this is the general behavior for any equation of state between 1 and 0. This is the case for equation of state between 0 and -2/3, and this is for equation of state between -2/3 and -1. So now we can focus on the physical branches, and we can compute the curvature. And then we see, so here we see that this is more or less what we wanted at the beginning, some kind of regularization of the theory. So for radiation, for instance, the energy density cannot go larger than this critical value. For matter, the energy density can grow as much as you want, but at higher energy densities, the curvature saturates and goes to a constant. And this is what we might hope to regularize the black holes indirectly. These lines, the dotted lines, are the prediction of what the results for general relativity. For this equation of state, what we find is that instead of going like rho at higher density, we go like rho squared. Okay, so now for these physical branches, we can play with p and rho and see for which values of p and rho we have a reasonable solution. So this is real and positive. And we find that the pressure should be smaller than lambda squared and plus squared. This is the free parameter in the action. And rho should be bigger than -4 on the square and plus square. So you should be. Now we are going to look at the cosmological solutions. So we take this Friedman-Lemaitre progression worker concept for you only need to take it for the space-time metric, and then you will find the auxiliary metric also has the FW form as expected. So you can compute the auxiliary metric. The solutions for M is the same because we will still consider a perfect fluid. So the results that I've shown before are valid. And then we find this relation between the scale factors in the two metrics and the large. Well, of course, the signature is preserved. This is because this is a positive quantity for the physical premises. So we can plot these factors, and well, you see that this is always the same. So for radiation, you always find this maximum energy density here, and yeah, for matter and cosmological constant, like almost, you have this tiny decay. So now we would like to compute the Hubble function, and this is where these funny couplings to matter is coming. So you take the Einstein tensor of the auxiliary metric, and this is defined like that. And now you can use the definition of M to express this in terms of M. So you invert this, and you express the Einstein tensor in terms of M. And now this is a function of rho and B. It's an auxiliary function, it's complicated, but it's a function of rho and B. Now you take the zero component, and that gives you the Hubble function, but for the metric tilde. Now you take this form, and you see, so this A, I remind you, is the ratio between the two scale factors, so simply this. And now for this, you transform the time derivative into derivative with respect to rho. I'm going to assume that we have a perfect fluid with constant equation of state. Otherwise, you will have here an additional term that will depend on the derivative with respect to P. So this is the simplest case. So you transform this into derivative with respect to rho, and then you have rho dot, and now you use conservation equation for rho, and you get this minus 3h rho plus P. You take out the h, then you obtain this relation between the two. And now you know that this is nothing but the 0,0 component of this. You put both, and you obtain this expression called the Hubble function of the space-time metric. And now this is a function of rho. I don't know if this clarifies your question.
But if you take for instance a scalar field, rho will depend on phi dot.
Yes.
So you
and
have,
then
the effective metric, which involves some.
So in that case, my guess is that you will obtain some kind. So you start from a canonical scalar field, you will end up with some k essence or something like that. So it will be a nonlinear function of phi dot because you have rho and p and all that, but that only depends on phi dot. So you will have higher, but it's a guess. Okay. And now it's also easy to compute the relation between both. So if you assume, well, this is usually the case, that the ratio between the two scale factors go like some power of rho, then you can use this here, and you obtain that h squared, this is a constant, if w is constant, of course. So h squared and h tilde square and h squared are proportional. Okay, now we can plot this function of rho, again, for radiation, matter, and the cosmological constant. So this is the result that you have over here. So we see that below, essentially 1. So this is rotated in units of lambda squared, m Planck squared. So here, of course, we recover GR, and then we see these differences at high energy densities. Again, we see this bound when you have radiation. For matter, h squared goes to a constant with the energy density of the dust fluid is very high, and again here it goes like rho squared. And this is what we are going to use now to develop this inflationary model supported by dust fluid, because here you have, well, h squared is constant, so that's the zeta. Okay, so it's not as easy as it looks. But, so what you have to consider essentially is that you have a bunch of dust components that decay into each other, and at the end they decay into radiation. Okay, I will explain later why you need all these all these components. So then you can solve the corresponding equations, and this is what I said. So dust goes like 8 to minus 3. This is h squared, and this is the, like, if you want the point regime, where h squared goes to a constant, and here we enter the general relativity regime, where h squared scales like rho. Okay. So now here they all scale like matter, of course, and when we abandon this high energy regime, then this decaying rates at some point will become larger than h because h starts decaying, and then the corresponding component will start decaying, and then another one will take over, and all that until all the components, or until the smallest decay rate is surpassed by h, and then all the dust components decay, and you're left with radiation. And this is because after inflation you want radiation to nominate the people. That's why you need to do this control. Okay, so now let me consider that all the decay rates are of the same order of magnitude, and then what you obtain is that they all decay at essentially one single time. This is to simplify some equations, but it's not really crucial for what I'm going to talk about. So in the cosmological phase, you can take this ugly function of h squared as a function of rho, and then you can expand for high rho, and you obtain this. So this is the Hubble rate during inflation, and this will give you this low rho parameter that you can compute, and is given by this. And I would like to point out that even though this is negative, this does not imply a blue spectrum because this is for this metric, and one should see the metric that the perturbations will see. Okay? And I will show the results for the tensor perturbations later. You will understand this. So we would like to compute the number of efforts of inflation, and then that's very easy because we know that inflation ends when raw matter essentially becomes order lambda squared and Planck squared. Or if you want, when raw matter is of the same order of h squared, because you are entering the GR regime, and then you should have the usual Friedmann equation. And then from here it's very easy to compute the number of efforts, and it's given by this. It depends on the initial amount of matter that you have. But there is a problem, that an upper bound, because this radiation component, even though it's dominant, subdominant, the pressure will be dominated by the pressure of radiation, because the dust components will not have pressure. Technically speaking, they will have a small pressure depending on the temperature and the mass, but I will assume that that's smaller than the pressure of radiation. Okay, so this is the initial pressure that we will have, and then it's 1/3 of rho, and rho of radiation will be essentially this quantity, because you need, so it's sourced by all these components here. And then, as I shown before in the physical region, in this plot, we saw that the pressure must be smaller than lambda squared and Planck squared. And from here, we obtain an upper bound on the number of efforts that we can have, and it's given by this. So it depends on the number of components and the ratio of the decay rates over lambda. And now we would like to compute the duration of this phase here. And this is very easy because here we are in the usual GR regime. So we know that a squared scales like a to minus 3. Then we take the value here, we scale, and we take the value here. And then you can compute the number of efforts. And again, it's given by this ratio. And now, if we remember the maximum number of efforts for inflation, we see that there is a link between the number of efforts for reheating and the numbers of efforts of radiation, and this depends on n. And then you see that for n equal 1, reheating is actually longer than inflation. And that might be problematic because you might end up finishing this reheating phase after BBN, and we don't want that. So that's what I'm saying. You should end before BBN, and for that what you do is you compute the rho radiation here, and you impose it to be bigger than rho for BBN. and then that gives you constraints on the initial amount of raw matter that you can have. Now you can take the discussion counts, right? We can say that we are going to saturate this limit, so we have the maximum amount of matter that we are allowed, and that when we take many components, intermediate components here, and we obtain this constraint on lambda, which is not very. So this is for the most optimistic case. Yeah, so now I will talk about tensor perturbations. So we take this answer for tensor perturbation, and for the matter component, it is anisotropic stresses. And then this is important that all the matrices that we have in the theory will commute at first order in perturbation theory and in tensor perturbations. And this is because tensor perturbations live in this box here, and all the background quantities for this box are proportional to the identity. So, and at first order you can only encounter products of background matrices with first order perturbation matrices. So they all will commute. This is good because it simplifies many computations. For instance, here these two are the same, so I can forget about this one factor. And then we take the tensor perturbations. This is invariant, so it's not perturbed. This is scalar. So this term does not contribute. We only have this, and we obtain this relation between the tensor perturbation, the fundamental matrix, and the anisotropic stress. Now we can go to the expression for the auxiliary metric, and the same. We obtain the relation between both. It's still the analogous for the auxiliary metric, where here we have to put still the scale factor. And then the interesting thing is that if we don't have any anisotropic stresses, the tensor perturbation in the fundamental metric vanishes. And then the tensor perturbations for both matrices are the same. And this is a result that was found in this paper by Bañados and Ferreira, but for the original Born-Infeld theory, where you have the determinant and that. They didn't consider anisotropic stresses, so they found this relation. And then we managed to show that there's nothing special. It's actually the case for any theory, the Palatine formalism, with this action. The only difference is that this function here will be different, and this is the function that will appear here. But the structure will be the same for any theory this time. Okay, now we can go back to the Einstein equations, and well, after some computations, you can obtain the tensor perturbations on the Ricci of the auxiliary metric, and it's given by this. And this is the same equation as in GR. Okay? Because you have this modified Newton's constant, and the equation is for the auxiliary metric. It's not for the space-time metric. So now you can just write down the equation, and then you can use conformal time for the auxiliary metric. We can assume vanishing anisotropic stresses, and we rescale the tensor perturbation like this, and we obtain the usual equation for tensor perturbations. The same equation as in here. The only thing is that in this case, the tensor perturbation is for the auxiliary metric, and it will see the expansion of the auxiliary metric, not of the space-time metric. And this is what I was saying. Even though the space-time metric will be inflating, that doesn't imply that this will be inflated. And actually, if you make numbers, so you can compute the effective evolution, but we'll see this tensor perturbation is given by this, where you can use all that, and in the end you will see that h tilde squared goes like a tilde to minus 6. And then you can see that this tensor perturbation will see an effective background with the equation of state 1. And this means that you don't generate tensor perturbations. Okay? Yeah, okay, I'm finished with it. So some things we would like to study further in this series is that the existence of bouncing cosmology. We know that they exist because Bañados and Ferreira showed for the original determinantal form. The problem there is that you encounter these tensor instabilities. we would like to see if with the other elementary polynomials we can have bouncing cosmologies without this problem. We would like to see if the gravitational study gravitational collapse and see if the black hole singularity can be regularized somehow. Of course, we have to compute the scalar perturbations in this dust inflation model. Tensor perturbations was more or less easy to compute for scalar samples. And we have to check the presence of instabilities. By this I mean like usual instabilities, not extraterrestrial. And then we would like to see the role of torsion in this kind of theories, because we always set torsion to 0. And yeah, at some point we would like to see, because usually at least the trace of the torsion in these theories arises as a Broca field, and that might have some interesting phenomena. Yeah,